domain theory of ferromagnetism. This theory was proposed by Weiss during 19th century. It explains the histories and the properties of ferromagnetic material. Magnetic domains, the boundary lines which separates two domains is called domain wall or block wall. When the magnetic field is applied to the ferromagnetic material, magnetization is produced by two ways. One is by the motion of domain walls, second one is by the rotation of domain walls. When you see the diagram, there are three diagrams. The first one, the dotted lines, indicates the domain walls. The arrow marks indicate the domains. In figure 2, when you are applying small amount of magnetic field, when you are applying small amount of magnetic field, the domain walls are slightly shifted towards the right direction. See here, the dotted lines are move away from the original position to the right, towards the right hand side. When you are applying large amount of magnetic field, which is not equal to zero, you can see the difference between the figure 1 and figure 3. The figure 2, what we have observed, the same observation is there in figure 3. After applying a huge amount of magnetic field, the domains also started for rotation. See, when you see these arrow marks, it seems like a circular motion. So this is the way when you are applying small amount of magnetic field and when you are applying huge amount of magnetic field, the domains and domain walls can be rotated. Further, it will be classified into different categories. First one is exchange energy or magnetic field energy. Second one is crystalline energy or anisotropy energy. Third one is domain wall energy or black wall energy. Fourth one is magnetostriction energy. First one is exchange energy or magnetic field energy. The interaction of energy which makes adjacent dipole align themselves is called exchange energy or magnetic field energy. The interaction energy makes the adjacent dipole align themselves. It arises from interaction of electron spins. It depends upon the interatomic distance. This exchange energy also called as magnetic field energy, which is the energy required in assembling of atomic magnet into a single domain. And this work done is stored as a potential energy. The volume of domain may vary between 10 power minus 2 to 10 power minus 6 centimeter cube. When you see the diagram, see the single domain. If you are assuming these positive and negative, let's say North Pole and South Pole. Similarly, when you are adding more number of single domains, the positive and negative signs themselves they have aligned. If one domain is spin down, another domain is spin up. Similarly, when you are adding n number of domains, spin up, spin down, spin up, spin down, it will go like this. This energy is called exchange energy. Next one is anisotropy energy. In a ferromagnetic material, there are two types of directional properties. First one is easy direction, second one is odd direction. What is easy direction? In easy direction of magnetism, weak magnetic field can be applied and odd direction will be classified into two different types, easy direction and hard direction. In a crystal system, we know that there are different directions based on the Miller indices. The planes are arranged or aligned in a different manner that will be defined on the basis of Miller indices. Okay, so we see the diagram in a graph along the x-axis magnetic field, along the y-axis magnetic field. When you are applying magnetic field on a magnetic material, how it will be magnetized? That will be plotted on the basis of their property. You can see the different directions 111, 110, 100. And see the curve along the x-axis when you are applying small amount of magnetic field, which is less than 16K. 111, 110 gets not magnetized easily. As compared to 100, the magnetization will be very less for the case of the first one and the second one. When you see this 100 direction and the lower amount of magnetic field, which is less than 16,000 Tesla, 100 gets magnetized. For the case of 111, 110, the same amount of value which was obtained by the 100 plane, the same value we have to apply 32,000 Tesla. Even applying 32,000 Tesla, then only we would reach the same value as we achieved for the direction of 100 at the lower magnetic field. So this is the way we can differentiate easy direction and hard direction. When we are applying lower amount of magnetic field, the direction which gets easily magnetized, that is easy direction, and when we need to apply huge amount of magnetic field, these directions are called as hard directions. Next one is domain wall or block wall image. Again you see the diagram, the domain walls. When you see the diagram, as we know that these arrow marks indicates the domains and the lines indicates the domain walls that we have seen in the last slides. A thin boundary or region that separates adjacent domain magnetized in a different direction is called domain wall or block wall energy. See, when we are moving from easy direction to hard direction or hard direction to easy direction, the way of the domain directions change in a particular alignment. We can see the transition zone. See, in a easy direction, if these domains are aligned in upward direction, when we are moving towards the hard direction in a crystal system, see the arrow mark slowly. Initially it was 90 degree, then 80 degree, 60 degree, 70 degree, 45 degree, then again minus 45, then 60, minus 60, minus 80, then minus 90. So again when you see the hard direction, all the domains were aligned in a perpendicular direction but towards the negative axis. So this change of electron spin in a transition of block wall. The size of the block wall is about 200 to 300 lattice constant thickness. We know that the value of lattice constant will be in the order of 10 power minus 10. So in a going from one domain to another domain, the electron spin changes gradually as shown in the figure that we have discussed. The energy of domain wall is due to the both exchange and anisotropy energy. Why we are saying exchange, which means in a exchange upward then immediately downward direction. Similarly here when we are changing EC to hard direction, there is a zone which is called domain wall. So this energy is called domain wall energy. So this is the way the energy will be classified.